thank you so much for having me here. My name is Kishimoto. I'm an assistant professor at the University of San Diego. I'm also a scientist at UCSD as well, and a veteran of just about every community college district that you've heard of. And it's really my pleasure to be here to kind of talk about some of the things that I'm a scientist, and it's just fun that every day that I get to teach. I get to kind of talk with students just like you about how nature works. But I also get sort of this fortunate thing where I get to just think about how the universe works, to read and to learn. And really, even though that it's my job to think and to learn of how the world works, in fact, we all have that opportunity. And so sort of that's really a neat thing about science, and I'm happy to share with you all the things that we do. So I am an astrophysicist, and sort of the first part, the astronomy, and typically when you think about astronomy, you think about really big things. And oftentimes you use the word thing, so there's no unit, which means anything big you could think about as being a really big thing. And so I want you to just take a moment right now. I want you to think about the biggest thing you can think of. And think about two of them. Right? Think about two of the biggest things you can think of. And now there's too many of you to call everybody out. So here's what I want to do. I want just everybody to out loud say those two biggest things they thought about. Okay, are you ready? Okay, on three, the two biggest things you can think of. Ready? All right, ready? 1, 2, 3. Okay. Did you hear that? That's okay. I heard everything that you said, because somebody said the universe. And that's right? The universe, actually, we stole that word from math, and the math people call the universe as everything. So the universe is everything. So sort of in a size and scale, it's the biggest thing you can possibly have. This is a picture that's called the Hubble Ultra Deep Field. So Hubble is the name of the space telescope. It's been out there in space for a couple decades, and we hope it keeps on going forever and ever and ever and ever and ever. But we've gotten some of the most beautiful and gorgeous and awe-inspiring pictures of space. Just about everything you see right here, except for this one thing right here. Every single blip and bit of light that you see here is something called a galaxy. A galaxy sort of initially thought of as an island universe. Hundreds of billions of stars, possibly many, many more planets, maybe people, who knows. But nonetheless, hundreds of billions of stars. And sometimes in astrophysics and astronomy, we get these numbers that are just completely blows your mind. 100 billion. I don't know what 100 billion is. If I had $100 billion, that would be awesome. I don't know what I'd do with it, but that would still be awesome, right? 100 billion, what that means is that if you had the time to count if you tried to count every single star in a galaxy, it would take you longer than a lifetime, even if you don't sleep, if you don't have nothing else to do. Right? That's a really, really big number, right? So this is the Hubble Ultra Deep Field. And here there are tens of thousands of galaxies. Right? Tens of thousands of galaxies are here. So tens of thousands of hundreds of billions of stars. Right? So just big numbers. Right? Just silly big numbers. And so we can think, well, how much of the universe is this? This is about, if you look out in the sky, it's about this big. Right? So look up at this ring right here. This is how big in the sky it approximately is. Right? So there's about 10 million of these in the sky. There's 10 million regions in the sky that are very, very similar to this. Right? The universe is a really, really, really big place. One thing I heard a lot of people say are stars. Right? And certainly a star is a good, right? This is, what's this? Right? This is the sun. Right? This is the biggest thing that's near us. Right? The biggest star, biggest thing that's near us. The sun is about 100 times bigger than Earth. This is a very, very highly energetic event on the surface of the sun. The sun is 100 times bigger than Earth. Right? What does that mean? That means Earth is like that big. The furthest you've ever traveled is smaller than that. Right? So that means when we're talking about the universe, not only is it tremendously big, but imagine the grand scales of energy, of all those big things you can think, right? Energy, mass, everything in the world you can think of. That takes to make these big arcs of gas that are much, much bigger than Earth itself. right? Astronomy is really the story of the very, very, very big. We can ask, how did we get here? How did we get to the point of having things like the sun? The story started, well, way back when, but the more immediate story started with a cloud of gas and dust. And when we talk about clouds of gas and dust, we use a unit that we call a light year. A light year is the distance that light travels in 1 year, which is much, much further than we'll ever travel in our lifetimes as all. Right? That's very, very far. Right? And nonetheless, these sort of pictures, you know, I have astro in what I do, so I think it's probably career malpractice if we don't have a bunch of beautiful pictures up here. And so, right, this is where the stars begin. Stars begin in these big clouds of gas and dust, encompassing clouds of gas and dust that are many more times than the mass of our sun. The sun is the biggest thing in our solar system. The sun is the biggest thing next to us. 99.9, etc. % of the stuff in our solar system, the things nearby us, is the sun. Right? Much, much bigger than us. And these are much, much bigger than that. We ask ourselves, well, what happens afterwards? Right? What happens? Well, we form a sun. It lives for a brief history of time, tens of billions of years, maybe. And nonetheless, what happens afterwards? Well, they find a way to explode. Whether it's a not so exciting explosion, as our sun will go at the very end of its lifetime to produce something like a planetary nebula that looks something like this, or maybe something like that, or maybe a star that are maybe 10 times more massive than our sun. So imagine that. The sun is the biggest thing that's nearby us, and there are things that are even more massive than it. Things that can live a lifetime of hundreds of millions of years. Now that sounds like a really long time to you and me, right? If I could live 100 million years, I'd be really tired by the end of that, right? But on the lifetime of stars, on the lifetimes of what happens in the universe, that's a very brief amount of time. But these really massive stars, they go through a completely cataclysmic event called a supernova. And just the explosion that ensues from that is just truly quite tremendous and plays an important part of why life is the way it is for us now. How did we get to be here? The supernova has a big story. Another word I heard out there in some of the biggest things you ever heard of is a galaxy, right? We talked about this at the very, very beginning. A galaxy is this conglomeration, this neat, sort of gravitationally attractive, this big, big, big thing with hundreds of billions of stars, probably hundreds of billions of planets, and who knows how many people, or people, I guess, if you wish. Right? Galaxies make up a large hunk of what we learn from very, very far away. Right? Why is it telling us what we know about what happens in this universe very, very far away? Because when you have hundreds of billions of stars, they can be really quite bright. And so when they're really far away, that's about all you get to see. So that's, sort of astrophysics is really the study of this really, really large thing. Right? Large things, from stars to galaxies to the universe itself. But in reality, a lot of what happens on these great, grand scales actually happens because of what happens at the most minute scale. Right? Actually happens at what happens in the tiniest of scales. And so now, just like before, I want you to take a few moments. I want you to think about two of the smallest things you can think of. Probably smaller than your younger sibling. Right? Two of the smallest things that you can think of. All right, got two? Okay, on three, I want you to just yell out two of the smallest things you can think of, and I promise I'll hear them all and put them all on my screen in just a moment. Ready? 1, 2, 3. Oh my goodness. When you get small, you get really small. And when you think about small, well, maybe it's something like a hair. Right? Hairs which are fractions of millimeters in size, right? Millimeter, that's small, fractions of millimeters in size. And we know if we go smaller than that, the hair is made out of cells, which might be a factor of 10 to 20, 30, even smaller than that. And we know that inside of cells, we have things like DNA, things like molecules that make up that. And as we look at the smaller and smaller, and we know that those molecules themselves are made of atoms. Right? And then we can think about, well, is that all? No. And maybe when you're in chemistry class, that's almost all. But in actuality, right, we go further, right? That atom, right? The atoms themselves are made out of 3 of our popular subatomic particles, right? What are those 3? Neutrons, protons, electrons. Right? You can break these things up, right? The atoms aren't so indivisible after all, because they're made out of these things called neutrons, these neutral particles that have a lot of mass in the middle. These protons, these positive charged particles that have a lot of mass held in the middle. And the electrons, which are they're just weird. They're so weird that artists get to do whatever they want. And we just let them do that because they're just weird. But even when we think about that, the proton still has a size, right? The electron, essentially, in all intents and purposes, has no size at all. It's a point, 0 dimensions. There's nothing there. When we think about a proton is, well, 1 femtometer. And what does a femtometer mean? It means a 0.00, about 15 zeros 1, well, 14 zeros 1 meters in size. Right? Absolutely tiny, but nonetheless, we have an idea of how big it is. And so if we look down deeper, those protons are made out of quarks. Right? We go down to the very fundamental sense of a thing that we call the Standard Model. We call it the Standard Model because the Standard Model describes the universe, describes nature at the smallest of scales. The Standard Model says that we have all these fundamental things. We don't think, well, we have not experimentally been able to make them any smaller than what they are. Quark, we haven't found anything experimentally way of making that smaller. Electrons, all these things, this description of the universe at the smallest scales, right? And so the particles is what we call it, sort of particle physics, is the study of the world at the very, very smallest. A lot of what we see in astrophysics, a lot of what we see on those biggest of scales, on stars, on galaxies, on how we got here to have the life we have right now, is really dictated by the really, really small. Right? It's really dictated by the really, really small. And so we can always ask ourselves the question, how do we know this? And if you don't ask yourself that question, you should start. Right? How do we know? Right? A lot of the things that we see in science, we've done our ways to do our best experiments to best understand what we did. So how do we know this? How do we know what matter is made out of? Well, how we know what matter is made out of is we take matter, we make them go as fast as we possibly can, and we smash them into other matter and see what comes out. It's like saying, what's this brick made out of? Well, all I need to do is take that brick and throw it at 99.9999999% of the speed of light. And when it breaks up into its constituent pieces, well, then I'll know what it's made out of, right? And so this is a picture of the Large Hadron Collider. It's a very, very large experiment. It's so big you can't even contain it in one country. Here, sort of in the border between France and Switzerland. And really, the whole goal of Large Hadron Collider are to take protons, to accelerate them, to speed them up so that they get to 99.99999 and so on % of the speed of light. So that takes a lot of energy. That's really, really difficult. And so what that means is they need to accelerate it over these very, very large tunnels. Tunnels so long they are tens of miles in size. That's a really big tunnel underneath the ground. And as they accelerate these, as they speed them up, really the goal is to make them go as fast as possible. And as they go as fast as possible, these protons, which I guess in this neat cartoon is supposed to be the combination of quarks, as they come on, they collide, and every fraction of a second in the experiment, one proton collides with another of proton, and a prodigious explosion of stuff happens. Matter, particles, these electrons and quarks and other things you might not have heard of, like the mu's, the tau's, the neutrinos, photons, all these different things that are a part of our Standard Model are created. So one sort of interesting thought of how science works is that, well, you've just took 2 protons and you've made a whole lot of stuff. And if you wanted to think about the old notion of mass, because we've seen mass before in a chemistry class in F equals ma, mass is something that we're used to seeing. But in reality, the mass that goes in of 2 protons is much, much less than the mass of everything that comes out. And it uses sort of that oft-quoted, rarely understood equation from Einstein, this notion of E equals mc squared. Right? Just nod if you've heard that before. Right? Even if it's in a cartoon, that counts. Or one of those sort of, punny type of cartoons where, anything. Right? Energy and mass. Energy can be used to create mass. And so what we do is from these collisions, from this sort of crashes at the prodigious level, we've been able to, as scientists, to build up this thing that we call the Standard Model. The Standard Model of physics is the most predicted, right? The most accurate, the best, if you want to use a word, the best physical model there is. And how do we know that? Because we can predict from our model what the experiments tell us. In fact, we can make measurements that are good to 14 decimal places. Right? So just, think about that. If you've ever sat in a lab, a physics lab, a chemistry lab, or anything like that, you don't even get 14 decimal places on your calculator to write down for which your chemistry professor marks the big red and gives you the old significant figures with the exclamation mark, exclamation mark. Okay, another exclamation mark and a frowny face probably. Well, I would give the frowny face, right? But nonetheless, right? 14 decimal place, right? So we've been able to really marry the notion of measurement and calculation, right? Lab and homework, if you wish, at sort of that prodigious scale, right? And so in reality, we've learned a lot. We've learned about how the world works by simply taking 2 things and crashing them into each other. But the universe, right, the biggest thing ever, it's also the biggest in so many ways. The biggest in size and scale, the biggest in time, the biggest in energy, in mass, in every single way. The universe provides us those most extreme environments that tells us how the world works. So that means as we continue to understand this, the best physical model we've ever had, though perhaps it's a little incomplete, eventually you can only crash these, eventually it's diminishing returns. Eventually crashing protons against protons or protons against antiprotons, or all the crazy things you can do in the laboratory. Eventually, you just can't put any more zeros, on the check that you write. Right? Eventually, it just doesn't get there. And so really, one of the neat things that I have found and that I've learned about astrophysics is that as we learn about this standard model, as we learn about how the way the world works, astrophysics can provide a unique environment. It provides the hottest, the most energetic, the most massive. It also provides very cold environments. It also provides environments where the physics of the very, very small are incredibly important to tell us about what happens on the grand and big scales. So let me take a few moments to talk about just what this standard model is all about. Right? We have this notion of a quark. And the quark is just the things that make up protons and neutrons. At least protons and neutrons are the things we're used to seeing. There's a whole bunch of things you can make with quarks. The problem is that they live for less than a fraction of a blink of an eye of a second. Which means in our everyday lives, we're not going to worry about it. In most even astrophysical scenarios, it doesn't even affect us. Only in the most craziest, of hottest, of most energetic of places do these things matter, right? So the quarks, you have this notion of an up quark and a down quark. And the ups and the downs make up what we're used to, right? They make up chemistry, if you wish. The protons, the neutrons are made out of up quarks and down quarks. Our chemistry also takes into account the electron. It also takes this notion of what an electron is. right? You've seen that before. It also includes this thing called the neutrino. And I'll get back to that in just a little while. But sort of as we build together this standard model, this way that we describe how the world works, it's really inviting us to think about the world in different ways. Right? It invites us to think about what happens when you take the things that you're used to thinking about and what happens at the fundamental level. And so I'd like to spend sort of my time here today to talk about a few astrophysical examples where really the physics of the very, very small plays on what happens at the biggest and grandest scales. So one thing that perhaps you've heard of and perhaps wondered what on earth the notion of that is this notion of dark matter. Dark is supposed to mean doesn't give off light. But in reality, what I've found in astrophysics is if we use the word dark, it really talks about our understanding. Dark matter, dark energy, dark other thing, the dark side. Oh. Right? It really ends up, right, we don't know what it is. So one of the weird things you can think about if you don't think about how science works is the very fact that I don't know. I don't know what dark matter is. Right? Any honest person who works on this doesn't know either. Well, that's not true. Everyone who works on dark matter knows what dark matter is made out of. We just don't agree with each other. And there's no experimental evidence that what we say is right. But everyone who works on dark matter knows what it is. But how do we know that dark matter is even there? Right? We can look at a galaxy, but from this galaxy, I don't see dark matter. You better not see dark matter because that's what the dark was all about. Right? So how do we know that it's there? Well, this picture, right, a picture of a galaxy, right, the light coming from a galaxy tells us so much. It tells us how the stars in those galaxies move. It tells us how the stars in those galaxies go around in circles, around and around and around and around. And as physicists, we like to say, well, we see things moving. And by seeing those things moving, we like to think we know not only where is it going to be later, but why it moved. Right? For example, if you just, I hope that's not on your test on Monday or whenever your test is. Right? Nonetheless, if you see something moving across the way, right, maybe you talk about how its position changes and velocity changes, acceleration changes, and all that. But in reality, it comes down to the notion of forces. It comes down to the notion of how the entirety of Earth below you pulled down on that ball as it traveled across the sky. And if indeed we measured that ball traveling across the sky, and we measured it as best we could, you could tell me. You can tell me something about how much mass, how much stuff there is in the Earth below us. And so likewise, as we look at these galaxies, by simply looking at how the stars move, we know about gravity. Gravity is the attraction of mass on mass. Matter attracting matter to each other. And so we can do this, right? It's actually not too hard, and if it's not too in-depth of a calculation, we can do it. And every time we do it, and then we say, well, where's the mass? Right? What's the most massive thing in our solar system? The sun. So a lot of the mass is in suns or stars out there. A lot of the mass is in clouds of gas and dust that we can see right here. A lot of the mass comes in things like that. And every time we add up all the things that we see, we always come a factor of 10 short or thereabouts. So that's not good. And I've been in your place too, right? You're in physics class, time's ticking down on the exam, and you're a factor of 10 off. I'm sorry, that's too close, right? You're a factor of 10 off, and then you're like, oh, wait, centimeters, meters, blah, 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 right? You're just racking your brain where that factor of 10 comes from. Well, the same thing here. But in fact, we've been doing this for a century. We've been doing that calculation between how much mass is needed to make things go in a circle and how much mass do we see, and we've always come up around a factor of 10 small. In other words, Newton's laws of physics, you know, that thing that you grow to love after you pass the class. Right? How do things work? How does the world work? Predicts that there's 10 times more stuff in this picture than you can see. Now that's tremendous. Right? Where is it? What is it? And what's more so is that this picture is right just so that. And even more than that, that 10 times more mass actually takes up a region that's maybe 10 times, well, 10, maybe 10 cubed if you want to talk about a volume, right? Very, very much bigger than that. We don't know what it's called, so we use dark. We call it a dark matter halo. It appears to be dark matter everywhere, you know, in this picture, going down classrooms that way and so forth. Right? But what is it? Right? How do we know it's true? Right? How do we know that our calculations just aren't wrong? How do we know that, well, Newton never did an experiment this big, so maybe he was wrong there. And Einstein didn't do an experiment this big as well. How do we know that? Well, we keep on observing. We keep on looking at what's going on in the universe. This is called the bullet cluster. So we thought about things like universes and galaxies, and there are things kind of intermediate in scale between those two. We call them clusters of galaxies, right? Large amounts of galaxies held together, large amounts of galaxies moving around each other, large amounts of galaxy with large amounts of gas. And these clusters of galaxies move throughout space. And occasionally, as they move throughout space, they crash into one another. And crashing into one another isn't as dramatic as it seems. Because the thing about a galaxy is that galaxies are extremely empty. Right? What does it mean that galaxies are extremely empty? Well, think about Earth. The nearest star to us is 100 million miles away, which is pretty far. Right? Many, many Earths fit between us and that. The nearest star is 1 trillion miles away. Very, 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 very million, very, 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 well, lots and lots of Earths fit between us and that. So if you think about one solar system and another system, when they crash with each other, it's largely empty space. So the galaxies, the stars themselves, just simply go straight on through. Dark matter. This thing we don't know about, except the only thing we know is that we can't see it. Which means it can't crash. Because when things crash, right, you hear it, or you see it, or you get something, right, energy. You can find about the energy that gets displaced when things crash. Right? So dark matter goes straight through each other. However, if you think about two large clouds of gas, right? In a gas, the spacing between molecules is tiny. So when clouds of gas crash into each other, they interact. And in fact, if clouds of gas crash into each other at tens of kilometers per second, so that's kilometers per second, right? That's thousands of meters per second. That's thousands, tens of thousands, 100,000 of miles per hour, right? I know I put it in miles per hour, and then I put such a big number in front of it, you just know it's fast. Right? But when they crash into each other, they get really, really hot. And so what this bullet cluster is really showing us is, first and foremost, all this pink gas right here, this pink diffuse thing, is what happens when clouds of gas crash into each other, and they just make this fiery mess of hot stuff. And fiery mess of hot stuff, we call those X-rays. Right? X-ray, we can look into the universe, we see them in X-rays. But if you look at where the galaxies, remember cluster of galaxy, right? Clusters of galaxies, they're here, and they're all the way out there. Right? The clusters themselves simply moved straight through each other. What's more, the dark matter. Remember that dark matter? The one where there's 10 times more dark matter than matter in our galaxy, and there's in fact tens of times more dark matter than matter in clusters of galaxies, which are thousands of galaxies, which is a big number. Right? In fact, we can tell that the dark matter is out there as well. And if you think for a moment, that statement I just said was hogwash. right? We saw the dark matter, right? That's wrong, right? Okay. So how do we know that the dark matter is there? Well, light, nature does weird things. And when you have a lot of matter, you have a lot of gravity. And when you have a lot of gravity, not only does it make, projectile motion, right? Everything that you learn about in the classroom happen, but in fact, light itself bends. Light itself changes its direction. And so what does that mean? There's so much matter. There's so much dark matter, so much that we can't see in these regions right here, that light itself bends from far off things as it goes through. So by looking at how much light bends as it goes through those regions, we know that's where the dark matter is. And we can see, once again, there's tens of times more dark matter than matter. Right? The universe is all dark matter. And so we can ask ourselves, well, how do we know this? Well, maybe we should start from an initial picture up here. This is the youngest picture of our universe that we have. Wasn't it cute back then? It's only 400,000 years old, on just a bouncing little young baby. And nonetheless, we can take that initial information and simply use what we know about how nature works and simulate forward. Simulate from up there, and it looks like it's really different between the reds and the blues, but the differences are 1/100,000th, right? 0.00001 different than each other. So slight differences in the universe became galaxies. Slight differences in the universe became stars, became everything up to you and me. So we can do these simulations. We can take it through the entire age of the universe. We can take it the entire 13.8 billion years since the beginning to today. And really what we can do is, as we simulate it, we can start to see what happens. We can start to say everything that we can possibly know. We put into this big computer code, and we run this big computer code on thousands of computers in parallel with each other for many, many, many months. And that's a lot of computing power right there. And we get an idea of what does the universe look like as it evolves. And if we just let it keep on going and going and going and going and going and going and going, what we can do is we can actually look at what you get. And what you get is you get galaxies that look like what we see. They will never be exactly like what we see because we didn't design it to do it that. Right? The people who did the simulation didn't design it to happen. But the galaxies look like what we see. And so while sort of this whole picture of dark matter, right, all the things about what dark matter is and how it got to here, we know that we have a rough idea. And that rough idea matches everything that we've observed about the universe. So dark matter is there. There's a lot to our universe that we can't see. There's a lot to the universe that we don't know about. In fact, if you do an average over the entire universe, there's about 5 times, on average, averaging big time, there's many times more dark matter in our universe than regular matter in our universe. Right? So that regular matter, that's the part that you do chemistry with. Right? The dark matter is many, many more times that. I guess the problem is we don't know anything about it. So what is dark matter? Right? When I wrote down the standard model, right, which is the best physical model ever so far, dark matter is nowhere there. And in fact, by looking at how the universe works, we know that dark matter is not there. Nothing in the standard model is dark matter. We know that. One thing is called supersymmetry. Anyone heard of supersymmetry? Right, a little bit of nods around it. Supersymmetry. And supersymmetry is this weird thing because it's super, which means we take everything in our standard model. We take our quarks and our electrons and our things like an electron and things called neutrinos and everything else. And supersymmetry says, well, what if we take everything that we know of and we copy it and make another one of it? We call them supersymmetric particles of that. And because we're scientists and we have absolutely no sense of creativity or originality, well, maybe not. Supersymmetry starts with S. So in other words, let's just take everything and put an S in front of it. So we got the squarks, and the selectron, and the smuon, and the stau, and the neutrino. And everything else, these other things that we like a photon or a gluon, or right, all these things that we have as part of our standard model, those other things we put an ino at the end. So there's a photino, and a gluino, and a xeno, and a wino, and a higgsino. But supersymmetry, for a long time, has thought to be, well, maybe one of these is dark matter. Maybe this is there. It's completely they have very little connection to what we see in nature, but maybe this is one of those things. The problem is as we've continued to look at this, we haven't seen any of this yet. Remember that Large Hadron, right, that big collider? They've been trying to see this, trying to see evidence that something here is there. Nothing. So what is dark matter? We don't know. And sometimes when you ask such an important question, like what is dark matter? What is this thing you just spent the last 15 minutes of my life on? And the answer is, I don't know. You might think that that's just a colossal failure of science. But from where I'm looking at it, that's what makes science awesome. Right? We don't know. But nevertheless, we can take what we understand of how nature works and continue to try to better our understanding to keep on working our way towards that. So dark matter, right? That's one way where the physics of the very, very, very small affect the very, very big. Something that I've done a lot of my work on is something called the neutrino. And the neutrino is sort of that forgotten part of the standard model. It's really hard for us to know, but nevertheless, we've got a poem. So John Updike, neutrinos, they are very small. They have no charge, they have no mass, and they do not interact at all. The Earth is just a silly ball to them through which they simply pass. Like dustmaids down a drafty hall or photons through a sheet of glass, they snub the most exquisite gas, ignore the most substantial wall, cold shoulder steel and sounding brass, insult the stallion in his stall, and scorning barriers of class infiltrate you and me. Like tall and painless guillotines they fall down through our heads into the grass. At night they enter at Nepal and pierce the lover and his lass. From underneath the bed, you call it wonderful, I call it crass. So the main properties of neutrinos are that they have no charge, which means they don't interact with other things that have charge. Right? They don't have that electromagnetic interaction that makes light. So it's really hard to see it. They have almost no mass. How much do they have? I don't know. We're trying. We're working on it. What's most likely the case is that we'll never find it in the laboratory. But maybe we can use the universe as a grand cosmic scale to measure it. But we don't know. And well, it's not that they don't interact at all, but they barely interact with things around us. Right? They barely interact with things around us. Every moment of every day of your life, trillions of neutrinos from the sun pass through your body. Every moment of every day. I don't care if you're asleep, in the building, at the beach, underwater. Every single moment, trillions of neutrinos from the sun go through your body, which is weird, right? Because the sun isn't there right now, it's there. Well, wherever west is. There, right? So what does that mean? It goes through the Earth because it barely interacts at all with that Earth. So now it sounds like a fairy tale. How do I know that neutrinos exist if they barely interact with anything at all? Well, step one, you better get as much stuff as you can. And when a neutrino, by accident, by slight luck of chance, interacts with it, you better be able to see it. So it's an ingenious solution. They built a humongous ball of water. And all around that ball of water, a bunch of cameras. And so what would happen is neutrinos come straight through. They interact with a single water molecule, just kind of by accident. Right? Very, very unlikely, but indeed it happens. Because there's lots of water molecules there. Right? I'll tell you how you win the lottery. Buy every ticket. Right? It's not buy every ticket to this, but right, we have a lot of chances right here to happen. And so when that neutrino hits a water molecule, it transfers some of that energy. It makes a bright flash of light. The ingenious part is that this is water, which means the light goes straight through all the rest of the water, and it reaches the cameras on the side of the vessel. Right? So not only is the water the target, the thing you ask it to hit, but it is also transparent to your signal, so you can see it. So let me show you the most expensive, probably, picture of the sun you'll ever see. Right? It's very easy to take a really bad picture of the sun. Just get out your cell phone and aim up and go. Right? But this is the sun in neutrinos. What time of day? It didn't matter. It was at all times of the day. You just added it all up, and this is what the sun looks like. Right? So trillions of neutrinos from the sun every day pass through your body. There's about a 1 in 4 chance that one of those neutrinos interact with one molecule in your body in your entire lifetime. So be worried. I will sell you neutrino insurance if you want. I will fix any problem that you can attribute to that 1 in 4 chance that you have, I promise. Right? There's really no influence of neutrinos on our lives. However, when we look in astrophysics, the most hottest and densest environments around, neutrinos can actually have a lot of interaction. They can actually affect a lot what's going on. Right? And so what else is important about neutrinos? Well, neutrinos are actually associated with the transformation of neutrons to protons and protons to neutrons. So here's my radioactive banana. An average radioactive banana creates 15 antineutrinos per second. Right? About 15 radioactive decays occur in an average banana per second. But what happens in that banana? Well, a neutron becomes a proton, and the result of that reaction created an electron, beta decay, and a neutrino. Right? So neutrinos are really important in our relationship between protons and neutrons. Why is it important to talk about protons and neutrons? Because of this thing. Right? All the things that make our life fun, if you wish. Right? If you think about carbon, which is you and me, right? Those things have equal number of protons and neutrons. Okay, that's neat. But something as we go all the way up to uranium, where there's about 50% more neutrons than protons. In other words, to make all the interesting part of the periodic table, you really need to start making a lot of neutrons. And neutrinos are the astrophysical way to do it. So I want to tell you a couple brief stories of let's go back to the beginning. Let's go to the beginning. Let me tell you a story about our universe. Way back when. Right? The universe started off in a very hot and very dense primordial soup. And that primordial soup, in the beginning, everything was there. The entire standard model. If supersymmetry existed, that might have been there as well. Dark matter, whatever that is, that's probably there as well. In the beginning, everything was there. Physics was just absolutely bonkers. Nothing like what we expect to see right now. The weak interaction wasn't weak. The strong wasn't so strong. Supersymmetry, who knows? Right? Everything was going on. In that first nanosecond, everything was there. In fact, in that first nanosecond, we expect the difference between what we call matter and antimatter was probably imprinted in our universe. The difference between you and me and anti-you and me, a proton and an antiproton, an electron and a positron, right? That difference was probably in the first nanosecond. How do we know what happened? We don't know. We think it has something to do with neutrinos. But you might just put the word dark in front of that, because we don't know. Right? We don't know. Okay, something happened. About a millisecond later, so just really, really long time later, a millisecond after the beginning of the universe, nature started looking the way we expect it to look. We had neutrons and protons. Dark matter was probably either there, whatever it is, or would be produced very, very soon. And in this slide, we have neutrons and protons, roughly the same number of neutrons and protons. The universe was still very, very hot, but we had neutrons, we had protons. But in fact, we also had neutrinos, we had electrons, we had positrons, which are the antimatter part of electrons, and photons around here. But in fact, there were 10 to the 10, so 10 billion of each of those per neutron on the street. Right? But really, the neutrons and protons were about the same as each other. But eventually, as the universe expanded, it cooled. As it cooled, the energy scales got less and less and less. And in actuality, the neutron is actually slightly heavier than the proton. Slightly heavier, about a fraction of a percent. And that fraction of a percent difference means that neutrons are more readily converted to protons than they are back. Which means about 100 seconds later, so I know, I've been yammering on about it longer than that. But 100 seconds later, the universe has cooled down, so there's a whole lot of protons and few neutrons. There's about 7 protons for every neutron. And we can calculate this and simulate and all that. Right? Well, after the 100 seconds, we started to do chemistry. We started to take these protons and neutrons and make actual elements, instead of just simply protons and neutrons. And what we did is, well, we went to the lowest potential energy state possible. We formed helium. Almost every neutron got captured into a helium atom. A small fraction became lithium, and a tiny fraction became deuterium, which is hydrogen 2, which is a nucleus that has 1 proton and 1 neutron. And about 400,000 years later, there's our baby picture. Remember all universe? And the universe was exactly like what we think, right? And here's our periodic table. Oh, I could do that chemistry all day. I could memorize that periodic table. I'd pass the test. Be a chemist after all. We had this. We had hydrogen 2, which is 1 proton, 1 neutron, which is what about 1 in 100,000. And lithium, which was 1 in a million. Right? This was everything. So, okay, that's neat. So we have a pretty good understanding of this, and our measurements appreciate that. But the neutrinos are really what have to do between going from equal number of neutrons and protons to having many more protons than neutrons. And we completely, this matches completely between what we've measured and what we've calculated, matches really quite well. The problem is that the measurements in astronomy are traditionally and famously not that great. The uncertainties used to be 10, 20, 30% in astronomy measurement was good, was great. But as we go on and build larger and larger telescopes, our new goal is a 30-meter telescope, which means think about a huge mirror 30 meters, 30 yards or thereabouts in size. Right? Really, really quite big. And from these, we think we can do a lot better measurements of, that. We think we can do even better measurements of this. So now we have to actually think about these neutrino things. And what turns out is the thing that's responsible from protons to neutrons and neutrons to protons are what we call the electron neutrino. They're what we call it, right? There's an electron, a mu, different things that are going on. Right? One of these 3 actually makes neutrons to protons and protons to neutrons. But we have 2 more. What we managed to find out is that neutrinos change. Between the 3 different types, they change. For all sorts of reasons, they change. Which means the way that these neutrinos interact with neutrons and protons to go to there is probably different than what we think. And how does that affect what we see? Good question. We're working on it. right? But our understanding of nature is getting tested by better and better observations. Our understanding of how nature works is getting tested continually by looking for the answers. But that's how science works, right? Science works by continually testing what we know, by embracing the I don't know, and keep on working from there. So I don't want to live in that world. I don't think my computer works, right? So what happens? For the next few billion years, we make stars and galaxies and all those great things. And somehow, that becomes that. And your chemistry exam just got a whole lot harder. But you get your smartphone. So you can decide if it was worth it or not. And so we ask ourselves, well, how did we get from there to there? Somehow we had to take protons and neutrons and somehow shove them together to make continually bigger and bigger and bigger and bigger things as we go from hydrogen, helium, and lithium all the way bigger than that. Stars are one good way to do that. Our sun will continually convert hydrogen to helium. Okay, that's okay. We already had helium. We need to get beyond that. Stars like our sun at the end of their lifetime might turn that helium into carbon, and maybe that carbon to some oxygen, which is good because we need to breathe. So that's good. Stars bigger than our sun might take that oxygen onto neon, and neon into magnesium, and so we can breathe and we can see neat-looking, neat lights. And might go on from magnesium to silicon to sulfur to argon to calcium. And each time it creates a new element, it gives us more energy. The stars get brighter and brighter and brighter until we get to the point of iron. And once we keep on working our way up to iron, all bets are off. We don't get energy. Eventually what that star does is, because it doesn't have energy, it collapses. It just starts free falling. It starts falling down towards the speed of light. And eventually the core of that star gets so tight and hard. And eventually it just can't compress anymore. And all that matter comes on in and it hits against the thing that doesn't bend. And it just goes back off. And we have this notion of what we call a supernova. And in that grand supernova, one of the brightest events we can ever see out in nature, a supernova outshines a galaxy. One star outshines 100 billion others, which is truly tremendous. And in this supernova, we think some of the elements can be created. So what happens? You have this big crash, and all this matter starts flying outwards, like that. There's one problem. When you simulate it, when we think about what happens, all that upgoing things, eventually it uses up all its energy, and it doesn't look like that. It just doesn't look like that. We do our best to simulate, right? We simulate this thing, this incredibly massive, incredibly large thing, and we just can't make it explode. How does it explode? I don't know. What do I know? 100 times more energy is released in neutrinos, these ghostly particles that don't interact with anything. So if somehow 1% of that energy, which sounds like a small number, I know, gets back into this, perhaps we can make it explode. Perhaps we can create all the elements that we know of. Perhaps we can get the things that we see, right? Nature is giving us a tremendous playground. Nature tells us, gives us the most extreme environments that you could ever imagine. Crazier than what you can do in your labs here. Crazier than what you can do in your labs at a big university, at a big, multi-zero funded laboratory. Right? Nature provides us these extraordinary opportunities to kind of figure out how the world works. And one of the neat things that I've been fortunate to think about in my career is, how does the world work? And to learn about how the world works by looking at the most extreme examples. And so I think we're right there at the end, like there. And so I think now is a decent enough time to take any questions that you might have. Thank you for your attention. Take questions or?